can call consistency. In the sense that, now let me comment. So let you suppose following assertions are equivalent. Following assertions are equivalent. First assertion is U subharmonic. So this, in which sense I'm calling this consistency? Because it says that as soon as we have enough regularity, then these two concepts are the same. What does it mean? It means that this second property is more general than the first one, but it is consistent with the first one as soon as we have enough regularity. So in this sense, this to be subharmonic is an extension of a classical subharmonic, and when we have enough regularity, the two objects are the same. So this is what I mean by consistency. Okay. The proof of this. Suppose that I want to show 1 implies 2. So what does it mean, classical subharmonic? It means that 1 means that minus Laplacian of u is less than or equal than 0 in omega. Okay. So we want to show that, that the function is subharmonic. Now, for subharmonic functions, we had the theorem that we made, don't remember, maybe last time or the lecture before, and it has 5 or 6 equivalent ways to say that the function is subharmonic. So I think that now we can use one of them. So let's see which one. So fix x in omega and take r smaller than the distance between x and the boundary of omega, and then consider the surface mean value formula, the surface mean value. So the mean value of the integral of u on the boundary of the ball centered at x of radius r. We can differentiate this with respect to r. And this is one of our first computations, I think several lectures ago. Remember, the idea was, let me quickly recall you. So what was the problem? Sorry. What was the problem? 1 Rn minus 1. Boundary of the ball. So the problem was that there was this dependence on R here, and so the idea was just to make a change of variable, transform this into the mean value over the ball of radius 1, and then here there is no more R, R is here, then we can differentiate, and then we can go back with the same change of variable At the end, the computation was that this was equal to 1 over r to the n minus 1, the integral of the boundary of PR, the normal derivative, no? Remember this? Remember this computation? It has been done a lot of time ago. Kahama? You remember this? Kahama?
Yeah.
Yes? You remember this?
Yes.
Okay. Fine. Then this also, maybe you should remember this other computation. We can transform this as an integral over BR. No? And of what? Can you remember this? I mean, this was one of the various. So using the divergence theorem, the integral of what? Here.
Maybe you, I think.
Maybe?
Itself, you.
No. I have to use the divergence formula, no? So let me record it. Let me quickly write it roughly. For a vector field eta. What is this vector field here?
Vector field, U is scalar field, just U, so its divergence is vector field.
No, you cannot do the divergence of U. You have to do the divergence of a vector field, no? Eta here is a vector field. So who was the vector field of those lectures? But you see it from here. I mean, this is the scalar product between the gradient of U and the normal, no? Do you agree? This is by definition. Therefore, which is the vector field eta? The divergence theorem.
Nabla U.
Perfect. Nabla U, gradient of U. And so here, the divergence of the gradient is the Laplacian. So we have this, and this we know. I mean, this has been done, I don't remember when, but a lot of time ago. Okay, so what do we find? We find that this is an old formula. We know that this derivative is therefore larger or equal than 0. Because the Laplacian now is everywhere larger or equal than 0. What does it mean? It means that this function has
monotonic with respect to R.
Exactly. So this function, so once we fix x and u, so the function R, not escaping out of omega, of course, R into this function S of u, x and R, is non-decreasing. Okay, so now u of x, you can compute u of x, because by smoothness, since u is smooth enough, in particular is continuous at x, we have that this is equal to the limit of as u x r, as r goes to 0. But this function is non-decreasing. Non-decreasing. So this limit as r goes to 0 is also the infimum. Do you agree?
Yes, here bigger than there. Here in the interval.
The infimum. Okay. Sorry, I another chalk because this is small. So is the infimum. Not simply because the function is monotone, decreasing, non-decreasing. And therefore, this is less than or equal than S U X R, because it is the infimum. So as soon as R is positive, this infimum is surely less than or equal to S. So at the end, we have shown that for any x in omega, for any R here, we have U of x less than, so for any x in omega, for any R in 0, omega x, we have that U of x is less than or equal to, and this was one of the characterizations of our of what we meant in that theorem to be subharmonic. So it was maybe by one theorem, by characterization theorem, I think maybe item A, the first item, characterization theorem implies that U is okay. Okay. Do you remember that the theorem that we had, I think, 6 statements equivalent. One was this, the other was the volume, mean value formula, the monotonicity of the volume. The other was the monotonicity of the surface mean value formula for some 0 R of x. Then there was the monotonicity of the volume from 0 R of x. And then there was another object that was relating to smooth sub and super solutions on balls or on relatively compact open subsets of omega. That long theorem. Do you remember this?
Yes, yes.
Okay, so Rama is okay. So if Rama agrees, we have shown that 1 implies 2.
Yes, yes.
Okay. So now let us show that 2 implies 1. Okay, suppose, so we know that U is subharmonic, and suppose that by contradiction it is not a classical, suppose by contradiction that U is not classical harmonic function. So, which means that there exists at least one point where this inequality is false. So there exists x omega such that minus at that point this is positive. Okay. Now U is C2, and therefore the Laplacian is continuous, and therefore this inequality remains valid in a small neighborhood of x. So there exists R positive, so between 0 and the omega x, such that the same inequality remains valid for any y in Brx. Now again we go and look at this object here. So now we consider again xr, and we show that if we do the derivative, now we do the same computation. Now we can do, because we have smoothness, so we can do the same computation. What happens if we do the same computation? the same computation in this small ball now, doing the same, making the same computation. Deduce that d over dr s u x r now is equal to this 1 over sigma n minus 1 r to the n minus 1 integral r of x Laplacian of u. And now we have that the Laplacian of u is strictly negative in the ball. So this becomes strictly negative. Okay. What does it mean? Well, it means that this function here as a function of r, the function here, what does it mean? Is strictly decreasing, no? The opposite as before. Before it was non-decreasing. I don't know where it is written. Okay, here. Now it's strictly decreasing. Okay. And now again, I think so strictly decreasing means that like this. Before, maybe it was with some flat region, we don't know. But here it is strictly decreasing. Okay, so now we look at u of x. So can you help him to conclude? Help me to conclude here. So what would you do? Similarly to what we have done before.
It's contradiction. It's a contradiction. What this one is supremo, then?
Exactly. So this is equal by continuity.
Yes, yes. Equal to limit, and limit is supremo.
Yes, exactly. So u of x is the limit of this. But now this is the limit as going to 0 is the supremum. R small enough. Let me not specify where is R, but for R small enough, S of u, x, and R. And this supremum now is strictly larger because we have that it is strictly decreasing. And this is a contradiction with our one of our equivalent concepts of being subharmonic. Because being subharmonic can be stated with this less than or equal to. Okay, so this is somehow this definition of the definition that we gave of subharmonicity shows that in some sense is a good definition because it extends what was clearly recognized to be, what does it mean, classical subharmonic. Okay, the first proposition of today. Then we can do some other theorem. Let's see if I can prove it completely. And this theorem is another one leading to another equivalent definition of the words another, besides the 6 equivalent characterizations that we have done in the big theorem, there is another one, of course, another equivalent of subharmonic. So we just prove an implication. I don't prove the 2 implications. I just prove maybe one, and I don't know if I prove it completely, but let's see. So let omega be an open set. Let U subharmonic then U is in L1 lock 2 minus Laplacian of U less than or equal than 0. Now maybe I should explain some meaning of the symbols, but let me erase something here. So this is proven, so we can erase. So everybody knows what does it mean L1 lock? I think so, no?
Yes, it's L1 function in any bounded ball.
In any bounded ball,
Yes.
contained in omega, yes. And what does it mean, the second assertion? Does everybody know? Or should I have to explain what does it mean that, sorry, this is just symbols, but this is in words, this is said in the sense of distributions. This so, do I have to explain? Maybe it is better, no?
It may be generalized functions. The second assertion in generalized sense, namely integral u delta phi is bigger than epsilon for any test function phi.
Less than or equal than 0. Now, however, there is a point here. Where is phi?
Test function is.
Not enough.
It's yes.
Not enough. We have a constraint on phi. This is important. So, let me try to convince you. What does it mean that I have a function satisfying a minus harmonic function in the sense of distributions? Means, as you correctly say, sorry, minus u. Oh, first of all, convincing Graham, the idea is to write some expression which does not involve any kind of derivative of u. So how can I motivate, why this one? So, well, you know, if everything is smooth, suppose u phi is smooth enough, I want to convince. Yes, I want
generalized derivative of u. It's
exactly.
Generalized sense.
I want to convince maybe all of you that writing this is natural. in place of this, so this is a pointwise expression at any point, but here in this sense is completely different. This is sort of non-local expression because it involves the function u everywhere in omega, not at a single point. But let me observe that maybe this is the first time, okay, what we are doing now in this course is just super classical theory, but the story is very long. We are just at the beginning, and all this kind of stuff becomes one of the ways to study this kind of problems in the Sobole space, in the sense of distributions, etc., which I have never mentioned here. And I will never mention, essentially, the Sobole spaces, probably. But let me convince you, because this will require another 15 lectures. And so if everything is moot, suppose that everything is moot, let me consider this, let me consider, so I know that, suppose that I have minus Laplacian of u equals 0 in omega, okay?
Integrating by parts, just
yes,
that integral.
Then I multiply by phi, test function. Test means here, as he was saying, test means C2, C infinity with compact support. This is crucial. So I multiply this, and therefore clearly this remains true. Then I integrate over omega, and this remains true. And now the idea is that instead of looking this with still involves two derivatives of u, and if u is not smooth, I can never write this kind of things. I try to use integration by parts. So integrating by parts, what do I get? There is a change of sign here. First change of sign, and then I have the scalar product. Scalar product of the gradient of u and the gradient of phi. Then I have, if omega is enough, I should have, say, I should have, but this is, I mean, it's not there, but I should have what, the gradient of u, sort of, I don't want to write it because I don't need, there should be a sort of normal flux of grad u phi, no? There should be something like du, d nu phi here. But I don't have it because phi has compact support. So it vanishes identically in a neighborhood of this set. So actually this integral is nothing but an integral evaluated on a bounded, relatively bounded open subset on the support of phi, say, in the closed compactly supported support of phi, and so this is not there. And I have first change of sign. But then I don't want to stop here. I do another integration by parts, and I recover the old minus here. And so magically, and I don't have any kind of boundary condition, again, for the same reason, because now my function phi is identically 0 in a neighborhood. So it is 0 with gradient identically 0 on the boundary, so there is nothing on the boundary, no any kind of... and so I end up with this. So this seems to be, then it seems to be reasonable to replace, if u is not smooth or we don't know, to replace the PDE, pointwise defined PDE, just to replace with this equal to 0 with the minus, for any now is not any point, any x, because now we have an integral, is any phi for any test function phi. Okay, this leads to the idea of, okay, well, why don't we think that this is a good definition of what could be a reasonable solution in another sense, called sense of distributions, or distributions, as Mirmukshin was saying, are also called generalized functions, even if generalized because they are, we frequently listen to the strange sentence that they are not functions, okay? Okay, distributions, okay. Now, so we accept this now, but the problem here, why all this this was trying to convince you that that is a reasonable definition, but the problem here is that we don't have an equality, we have an inequality. So what do you think that we need to add to our test function in order to do the same path? I left some space here, open space. I should add here something on my test function. What do you think? What do you think?
Sorry, can you repeat? Can you repeat? Your question was?
Yeah, my question is, you see, if I am allowed to change the sign of phi, I can make this negative, and non-positive and non-negative at the same time. So this means that if I allow this to be true for any phi, as you are suggesting, then I immediately get this. My comment. What does it mean? Because I can always change phi into minus phi, no?
Yes, we can change.
If I am allowed to change phi into minus phi,
then it must be equal, not inequality, equality.
No, I mean, if I allow phi to exchange into minus phi, this inequality change sign.
Bigger than 0, then
and
we
so
have
this means that
two inequalities at the same time.
It becomes equality.
So it must be equal.
Yeah, but this is not what I want to do. Because for me, the inequality is crucial. I'm speaking about subharmonic functions, not harmonic.
Yes.
So,
yes. In that case, it is harmonic function.
Yes. But I don't want to do that. So I want to keep subharmonicity. So what kind of other constant I have to add on phi?
Maybe we consider some con, not full phi, some cons.
No, I mean,
con means
is the simplest way to
phi bigger than 0. We add some condition.
Oh, yes. Non-negative. Phi compactly supported smooth in omega with non-negative values. In this way, I am not allowed to change phi into minus phi, and then this is a reasonable definition, okay? So this is what I mean in 2. 2 means this.
Okay.
Clear, Rahama, for you, which means this. So this is a partial differential inequality in the sense of distribution. Okay? Is this clear?
Yes.
Now I'm asking also Rahama. Rahama?
Yes.
Okay, perfect. So, so this is what I meant, and then let's see. So what I'm saying is that if I have a subharmonic function in the 6 senses, equivalent senses of our theorem, then it also satisfies this. And actually, it is possible to prove essentially also the converse. So this 1 and 2, one more comment, sorry. Why it is natural to ask L1 lock? Why it is natural to ask L1 lock and not, for instance, L1 or L2 or whatever? This is another important point for understanding the meaning of to embed the L1 lock functions in the universe of distributions. Why L1 lock and not L1, L2, LP? Why there is a lock and why there is a 1 also? No? Bookchin, do you know why there is L1 lock? why it's natural, say, to ask L1 lock?
No, I have not answered.
Okay, let me try to convince you, but just because it is the natural assumption to do in order this integral to be converging. Why? Because this integral here is reduced to the integral over the support of phi.
Yes, bounded set.
Which is a
compact set, bounded set.
Which
yes.
is a compact set. So this must be true for any phi. So this means that this integral must be converging if I put here any compact set here without this. And
yes.
so,
then integral has some mean. If it's not.
So it means that if I have any compact subset of omega, we need essentially this to be finite.
Yes.
For any compact subset of omega. This is just to give, to be sure that this is well defined. Just because this integral is reduced on the compact, on the support of phi, that we know it is a compact set, and then this must be well defined in the sense of Lebesgue, etc., etc., etc. And therefore, this is the natural, remember, is the natural, the lock is important, and it is the natural thing to say. Okay. So let me erase the things and try to start the proof. This last remark, sooner or later, I don't know what you will do. What you will do in your next years of your studies, but this L1 lock remark is useful for you if sooner or later you will study distribution theory, because essentially it helps to understand why, in which sense all L1 lock functions can be considered as distributions. I don't want to tell you anything more, because otherwise I should define what is a distribution, etc. But essentially, distributions are certain linear functional on this space. And one can embed L1 lock functions, can be embedded in, considered, there is an injection, any U in L1 lock induces a well-defined distribution, and the distribution is nothing but exactly U phi dx, which acts linearly on a smooth compactly supported function. Compactly supported is important because this must be well defined, and in order to be well defined, this is the natural space. So we have an injection, in some sense we have an injection between this space of functions inside a space of linear functionals on a function space, etc., etc. So sorry for this parenthesis, maybe not useful, but okay. Okay, so let's try to prove this proof. So first of all, we have to show that for any k relatively compact in omega, the integral finite. We have already observed something in this direction. Do you remember?
Yes, upper semi-continuity implies.
Implies what?
Upper semi U plus.
Yes, exactly.
Bounded.
Observed that because remember u, we can write u as the difference of two functions, non-negative functions, and u plus and u minus, and we know that u on a compact set being upper semi-continuous has a max, a finite max, and this max therefore bounds u plus and etc. So we already observed. So we need to show in view of this, we have to show actually only that this is finite. We only have this, because once we have that this is finite, then no. Once we have this, since the absolute value is the sum of these two non-negative functions, also the integral of the absolute value of u will be finite. So, and let us introduce a set here. Okay, maybe we can suppose that omega is connected, just to simplify. Because we can do this argument on any connected component. So, since the argument the next argument can be repeated on any connected component of omega, we shall assume from now on that omega is connected. Okay, so now introduce a subset, call it capital A. There exists neighborhood X such that capital U, Okay. Then showing that U is in L1 lock is equivalent to show that A is equal to omega. Okay? By definition of A. So we have various things to prove. So we have to show various things. One, A is non-empty. Two, A is open, the relative topology of omega. Well, openness is a direct definition, a consequence of the definition. A is closed in omega, in the relative topology. What does it mean? It means that so we have to prove these three things. Where now the second one is a direct. Okay, this may be home. Okay, so now the point is to show that this is non-empty, and that it's also relatively closed. Okay, so omega is connected. We know by definition that u is not identically minus infinity in omega. This was one of our definitions. So we can take a point so we can take a point x naught where u is not where nu is not minus infinity. Okay. Now we can use one of our definitions. So take for any r n, for any r 0 the omega of x naught, what do we have? We have minus infinity less than u of x naught less than or equal than the volume mean value formula, all 1 over omega n r to the n r of x naught of y dy. Okay, and now what do? We simply write this as 1 over omega n r to the n integral plus y dy minus 1 over omega n r to the n minus y dy. So this is finite. And then this means that also that object must be finite, cannot be minus infinity. No? So this also must be finite, because otherwise, if this is plus infinity with the minus is minus infinity, and we get a contradiction with this. So, yes, so dr of x naught minus of y dy cannot be a non-negative finite number, and also this is a non-negative finite number, and therefore we have found that in BR u y finite, and therefore x naught is the point of A. Because there is a neighborhood, open neighborhood of x naught where u is absolutely integrable, and so x naught is in A. Okay? Clear?
Okay. Yes, it's clear. Second is just trivial. Second, A is openness of A because we get, for example, for X, V is that open neighborhood, then what? Any neighborhood, any point in this neighborhood clearly is just element of A, because that point we can get also same neighborhood,
yes.
V.
So yes, this is easy. It's not difficult, I would say. So we have shown this one and this one. So what remains to show is this. More difficult. So let us take a sequence now. So let me erase. I always erase. I don't know, maybe I can leave you some detail on the next proof. I don't know, because it's not easy. But I am also realizing that I am running out of time, and probably I will even not be able to reach the Perron solution. But okay, let's see. I don't want to, I don't know. Okay, what remains to show is that A is closed. So let's take a sequence XH. Let's say sequence of points of A. Suppose that xk converges to some point x infinity omega. We need to show that x infinity belongs actually to A. Okay. So maybe I can give you some hint to do this. Otherwise, I am still at point 1. So xk in A means that there exists, remember the definition of A, that there exists an open neighborhood of xk where u is in L1. So there exists some radius small enough such that the integral rk xk u. Okay, now inside this ball, take now for any k. Okay, so x infinity. Define r the distance between the boundary of omega and x infinity, which is positive. And then take a point yk for any k. Yk in B rk k, where u of yk, you can say yk distance from xk less than 1 over k, for instance. This is even not necessary, actually. Okay, so, and then this is okay. And then I ask you to fix k bar n such that yk bar minus x infinity less than r over 2, so that so we have this situation. We have this is omega, say this is x infinity, this is the distance, let me call it r. Then I have yk here, xk is converging here, and yk also. Yk is converging here somewhere. Yk minus x infinity, so this means that x infinity belongs to the ball of radius yk bar and of radius yk bar, of radius r over 2 centered at the yk bar. So, and the idea is to show that so we have found an open neighborhood of this limit point. It's enough to show that it's in this, in order to show that x infinity is in A, it's sufficient to show that, so in order to show that x infinity belongs to A, it is sufficient to show that the integral of the modulus of u inside this neighborhood is finite. Over 2. Okay. And for this, actually, for this, okay, for this, use the previous argument, use similarly as before. So, I mean, this maybe is really useful. Then this is less than, and then this is less than or equal than the volume in value formula at yk k bar r over 2, sorry, of u, of u yk bar r over 2. So it's not difficult in a sense. You have to redo similar argument as before. I mean, this is the path. Now fill the details if you are able. Otherwise, okay, I will write them. Or if you want, I can do this tomorrow. Try to fill by yourself. So what remains to show now is point 2. This I want to show you instead. Point 2. So in point 2, we will do this by sort of convolution argument. So fix epsilon positive. And take rho epsilon, the standard sequence of standard radial smooth compactly supported modifiers. Sequence of standard smooth standard radial compactly supported modifiers. And now we work in omega epsilon minus. Work in omega epsilon minus, which is just the reduced of epsilon of omega. So it's the set of all points of omega at distance from the complement larger than epsilon. So it is just to give a meaning, since the support of rho epsilon is centered at x is a ball of radius epsilon centered at a point, then in order not to go outside of omega, we need to do that. So take x in omega epsilon minus. And we consider u epsilon, which is the convolution. This is well defined, as I said, in omega epsilon minus. This you know, no? Okay. No. Define u epsilon, the convolution of u, where it can be defined. So let us show that u epsilon is subharmonic in omega epsilon minus. Okay. Let's show that, well, this we can do in various ways. We can do, for instance, using the, I don't know how much you know on convolutions. Do you imagine? Well, okay. Let's do the computations. So let's write the surface mean value formula for u epsilon centered at x. So the surface mean value formula centered at axis of radius r, say x and fixed radius r and the less than the omega epsilon minus. So let me write this expression. So this is 1 sigma n minus 1 r to the n minus 1 integral of the ball of radius r at x u epsilon of y y. Now you have to substitute the expression of this. R to the n minus 1 integral boundary of BR of x. Now I have the integral over the epsilon u 0, say. Now this is in y, so z minus y, rho epsilon of z, y minus z if you want. Epsilon of z dz dh 1 of y. Do you agree? Maybe, yes. Do you agree with this?
Yes, because support of rho epsilon is in the ball.
Yes. So this is okay. Now, just writing what is the convolution. Now I can exchange the integrals. So 1 over sigma n minus 1 r to the n minus 1 integral of b epsilon 0. This is z. So we have rho epsilon of z, z. Now we have the integral over the boundary of BR of x u of y minus z hn minus 1 of y. Okay. Now what do we know? We know that u is subharmonic. So for any z, the map for any z in B epsilon 0, the map y into u y minus z is subharmonic. Harmonic omega epsilon minus, where in its domain, say. So since this is still subharmonic, then we can...
The inequality holds. We had inequality.
We have the inequality, exactly.
After that, just modifier integral equal to 1, if we estimate is inside that integral.
So at the end, what do you get? At the end.
At the end, at the end, one.
Exactly. Exactly. At the end, I mean, let me write it maybe also for the others. So let me do one more step. So 1 over sigma n minus 1 r to the n minus 1. This is the mean value as x, u of y minus z, dh n minus 1. And then I have this final rho epsilon z dz, no? Now this is the mean, reminiscent of course of the mean value. And
bigger than ux minus z?
Yes, exactly. This is larger or equal than u of x minus z at the center. Because, yes. Because this is just the mean value, so by this remark if you want.
Yes, just center shift.
Okay, so what does it mean? It means that after all these computations, this quantity here is larger than or equal to this quantity here is larger than or equal to
convolution.
Be epsilon 0 u x minus z rho of epsilon z dz. Okay? Okay, and now I think I made some.
We pass to limit. We have to pass limit as epsilon goes to.
Yes, because no, this is the
0.
definition of u epsilon, no? By the way,
Yeah.
it's the convolution. So this is u star rho epsilon. Yes. So we have u epsilon of x less than or equal than this. And so the idea is using the property of convergence for the convolutions to pass to the limit as epsilon goes to 0. No?
It L1 converges, and this modifier converges L1 to U, and it almost everywhere converges also at all Lebesgue density points of U.
Yes, 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 yes. Okay, let me write it here. For any x in omega epsilon minus epsilon of x is less than or equal than s of u epsilon xr. So what does it mean? It means that u epsilon satisfies this, but we know also that u epsilon is smooth, no? Because it is a convolution, this you should know. So u epsilon is smooth. It satisfies this by the first proposition of the lecture, the proposition at the beginning of the lecture, since we have smoothness, this is equivalent to say that minus Laplacian of u epsilon, now this is a smooth, it's a classical subharmonic function, no? Do you agree? This is, I am using directly the first proposition that we did, the consistency, the consistency, by the consistency. They called consistency. Okay, so this means that we have that inequality, but now the path is easy because we can multiply by a non-negative test function. So now we can multiply.
Yes. Still negative.
Take phi negative. And so this means that we have minus Laplacian of u epsilon phi dx less than or equal than 0. Now we can pass to the limit using the properties of convolutions. Passing to the limit gives, fill the details. This is easy. You can pass to the limit and you get for any, say, omega prime, you get minus Laplacian of u phi dx less than or equal than 0 for any phi test function, and this is true for any omega prime. I mean, fill the details here. This is not difficult. I'm realizing I'm a little bit out of time, unfortunately. So anyway, this I hope to convince you that all the story somehow is closing in the sense that we are actually we could add another equivalent, at least half of another equivalent definition of subharmonicity. Okay. Now there is another big part that we have before going on toward the Perron method we need to fill, which is a very important part that is missing, and it is called the Harnak inequality. And this requires a not so short discussion. It requires a not so short discussion. Somehow related to the gradient estimate, but it's a different inequality. And then I have to think about how I have to tell you in not too many times. So let me see. So the Harnak inequality, so well, maybe it's the last step missing toward the Perron method. Maybe. So, but this is interesting by itself. I mean, even if without the out of the Perron method, it's very interesting by itself. So Harnak inequality. New chapter. So let me start maybe from the first way, sort of optimal way. Okay, this, remember, this always holds under a new assumption. So remember that this, when you have Harnak inequalities, you have, typically you will be concerned with the assumption on the sign of U. Okay. Okay. So now let. Okay. Did I? U. Harmonic. Ball. So let me take it BR0. So let me call it BR for simplicity. Yes. And let U be larger or equal than 0. Let R be a number, intermediate number between 0 and R. Then we have this pointwise so you have two balls, one inside the other. Actually, we will need a third ball, but okay, so this is the origin. R. You are controlling the value of Ux in this smaller ball to some constant which blows up as R becomes capital R. So it says, in some sense, this inequality says that the values of U in the ball are all in this ball here are all comparable. You cannot have two big oscillations between values of U for a non-negative function U. Okay. Now this inequality here is fundamental for studying. Let me just mention this. Fundamental tool together with the gradient estimates. For studying regularity theory. Well, we know that harmonic functions are analytic, but these kind of inequalities are fundamental for more general PDEs. We will see that this will be a consequence of our Poisson formula. So let's see. Did you understand? I mean, the meaning it's somehow maybe at the first sight a little bit mysterious, no? But this sort of that is the inequality. N is larger or equal than 2.
You omit in the first inequality, I think, just U0.
Yes, you're right. Sorry. U of 0. Okay. Now the proof is tricky. Because we have to cleverly use our what we know about the explicit solution of the Laplace equation on a ball. So we fix an intermediate radius here. We have 3 concentric circles. So this is rho. And then at the end, this rho, at the end, let rho toward capital R. But this, now we fix it for a while. Okay. Now we can apply the Poisson formula. And use our Poisson formula. Remember the Poisson formula. The Poisson formula says that we are able, through the singular kernel, which was called the Poisson kernel, to express the value of a harmonic function at all points inside the ball, all points, not only the origin, all points, by means of a sort of using the kernel of U with some other factor. So let us write it. We can use the Poisson. Oh, first of all, U is harmonic, so U is C2 up to the closure. Since U is harmonic R, and since rho is strictly smaller than R, and U is harmonic, and therefore C infinity, as we know that U is certainly C2 up to the closure of B, the intermediate radius rho. Okay. You can use the Poisson formula integrating over the intermediate, integrating over the boundary of B rho at all points of the smaller ball. So we can evaluate the value of U inside the smaller ball, integrating instead on this for any x. So what does it mean? It means that we know U of x for any x in BR closure. No, do you remember is rho square minus x square Then we have some factor which is easy to forget, but we have at least rho. And then what do we have here? Sigma n minus 1 integral b rho of the origin. Here I'm fixing the origin 0 for simplicity. Of course, everything holds with the proper translation. So here we have u at any point, proper translation. So here dh and 1 correct? And check because this constant here, but I think should be correct. Okay, now what is the situation? So we have this, no? And it's enough actually to use this formula for x. Let's start from taking x on the boundary. So x is here now. Okay. So in particular, we can employ this formula. Use formula, Poisson formula for any x on the boundary of BR. Smaller ball. Remember that this is an estimate that we want to do in the smaller ball, in the closure of the smaller ball, of course. So our x is confined to stay here. We use this just as a tool to produce the formula. Then this rho will disappear going into capital R. So we are interested to estimate u of x inside. But remember, since u is harmonic, we have the maximum and minimum principles. So it means that if we are able to estimate u of x just on the boundary, then the same estimates will be true inside of the small ball. No? So
yes.
So the idea is exactly to do an estimate now, confining x here on the boundary. Okay, let me draw it maybe with another color. So x will live for the moment just here. Y is a point here. Because y is running in the intermediate ball that we are using for our technical purposes. Then it will disappear.
We can estimate in the denominator inside the integral. This denominator less than
exactly.
1 over r. Yes.
Yes, exactly. This is the idea, because there is some space between x and y. Okay. What does it mean there is such? So you see, we have to so let's take x equal. So let's take x equal here. So this means that x is equal to r. Not only this, but as he was saying, we can now evaluate this length. We can estimate this length. So this length, x minus y, is larger than what? Okay, is larger, if you want, larger than y minus x. But it is clearly larger or equal than, so I mean, the most lucky situation is when they are here, no? So it's larger or equal than this rho minus small r, okay? Larger equal rho minus r, okay? So now this means that one of this is less than or equal than 1 over rho minus r, okay? And this means that we will try to prove just this part of the inequality, okay? Just this part. You can imagine how to try to show, but maybe we will see this tomorrow, or I can leave you as an exercise. If I want now, if I want to go into this direction, I have to bound this from above, and so this from below, okay? In any case, so let's try to go on, even if time is almost finished. So now we have bounded this, so we have that for any x and y there, 1 over x minus y to the power of n is less than or equal to 1 over rho minus r to the n. And now I would like to write this inequality, no? I would like to write this less than or equal to rho square minus, now x is on the boundary of the small ball, so is equal, this modulus, the absolute, the modulus is r. Okay, then, so I just substitute. Now I would like to use this estimate. So can I do that? 1 over rho minus r n integral boundary rho 0 y dy. Can I do this or not? Question.
First, u is harmonic function.
But can I do this inequality?
No, this second, it's surface mean of this
Yes.
integral equal. It is the surface mean of u. So there is some equality here. It's equal to the value of u.
Yeah, but
at the origin.
But don't we have to use some assumption here to have this inequality, or not? And there is one assumption that I have not yet used here inside my statement. Can you see it? What kind of assumption am I using?
No, sorry.
Rahama, can you read the statement? There is an
U is
assumption.
non-negative.
You?
U is non-negative.
Yes, yes, thanks. I am using this assumption, no? In order to go on. Okay. So, then now we can use the surface mean value formula. You can multiply and divide. We will continue tomorrow, but this rho minus r kills with this, so it remains rho plus r divided by sigma n minus 1 rho. Here we have rho minus r to the n minus 1, because 1 is killed by this. And then maybe I can multiply and divide by sigma n minus 1 rho to the n minus 1, 1 over sigma n minus 1 rho to the n minus 1, the mean value. And we will see tomorrow, but this is just to have a surface mean of u. So this will be u of 0. And then we have to arrange these terms. We are not far from the end of the proof, at least of this part of the inequality. Then the other must be, as I said, you have to use another inequality from the other side. We will do this, we will continue tomorrow to maybe to the details and to go on in the direction of the Harnak inequalities. Okay, so this is all for today, and tomorrow at 2 o'clock, I think, we have the lecture. Thanks, and see you tomorrow.
Thank you.